Exponential sequences. Exponential functions of the form y equals a times a to the power of x, where a is the initial value and a, the lowercase a, the multiplier, common ratio, produce geometric sequences. Consider a ball dropping from a height of 10 meters. So we have our x-axis and our y-axis, and at 0 on the x-axis, we have a point at 10 on the y-axis. So that point there is 0, 10. So this is where the ball is dropped. It's dropped from a height of 10 meters. If the ball bounces back to 2/3 of its original height on each bounce, the height of the ball is given by the following pattern. So after one bounce, 10 multiplied by 2/3, or 2/3 of 10, is equal to 10 times 2/3 to the power of 1. So after one bounce, the ball comes up to about here. It bounces back to 2/3 of its original height. So 2/3 of 10 is 6.666 recurring. So we'll say 6.7, we'll round off to 6.7 meters. So that point there is 1, 6.7 meters. Now we're not interested in the 6.7. What we're interested is the 10 times 2/3 to the power of 1. That's what we're interested in, but that's what it gives us, approximately 6.7. After two bounces, 10 times 2/3 times 2/3, so it's 2/3 of the previous bounce, basically 2/3 of the previous height, is going to be equal to 10 times 2/3 to the power of 2. So that's this point here. So it's approximately, so it's 2 on the x-axis and approximately 4.5 on the y-axis. So this point here is 2/3 of the previous height. So the previous height was 6.7 approximately, and 2/3 of the previous height is about 4.5. And the process continues in that way. So after 3 bounces, it's going to be 10 times 2/3 times 2/3 times 2/3, which is really 2/3 of the previous height again. So that's 3 on the x-axis and 3 on the y-axis. So this height here is about 2/3 of the previous height. So this is the previous height here. And this is about, this point here is 2/3 of that previous height. So that's represented by 10 times 2/3 to the power of 3. And after n bounces, we're going to get 10 times 2/3 to the power of n. So for example, if you were interested in the height after 7 bounces, you would do 10 times 2/3 to the power of 7. And we can see 7 on the x-axis is here, and the point that it corresponds with is probably around 0.7. So that point there represents 2/3 of the previous height, which would have been the height at 6 on the x-axis, and so on. So we start off with a height of 10. The next height that the ball jumps up to is 2/3 of the previous height, so 2/3 of 10. The next height it jumps up to is 2/3 of the previous height again, and the next it jumps up to is 2/3 of the previous height again, and so on. So we can see we have this curve forming. So this is an example of an exponential graph, and it started off very high up, and we can only see 0, 10 on the x-axis, but we can imagine that it started much higher. Not the ball as such, but just the graph that represents the pattern of the ball bouncing. And then we can see that it shoots down, and then it gets closer, very gradually gets closer to the x-axis, but it doesn't actually touch the x-axis. So here we have 2 more graphs. So this is some function, f of x is equal to b to the power of x. So we don't know what the numbers are, but the important thing here is that b is somewhere in between 0 and 1. So this represents exponential decay. So this is a similar graph to what we had a minute ago. So it starts off really, really high, and then it jumps down, and it very gradually then starts to get closer and closer to the x-axis. This graph here is, again, as f of x is equal to b to the power of x, but this time the b would be greater than 1, and this would represent exponential growth. So if the b is greater than 1, we can see it starts off very, very gradually, so it's very, very close to the x-axis, and it gradually gets bigger and or higher and higher, and then it shoots upwards. So there's another example of an exponential graph. So these two graphs here, they're a mirror image of each other, but the important thing to note is that the b is between 0 and 1 for the graph on the left, and the b is greater than 1 for the graph on the right. So here's example 6 of exponential sequences. A ball is dropped from a height of 27 meters and loses 2/3 of its height on each bounce. Find the height of the ball on each of its first 4 bounces. Hence, so using what you worked out in part 1, write down the height of the ball after the 10th bounce, and after which bounce will the ball be at most 2.5 meters above the ground. So term 1, after the first bounce, the ball is 27 times 1/3, which is equal to 9, so 9 meters above the ground. Now just be careful with the third part here, because we were told in the question that the ball loses 2/3 of its height. So loses 2/3 is the same thing as the ball bouncing back to 1/3 of its height, because 1 minus 2/3 is equal to 1/3. So just be very careful with the phrasing of this question. So you might have thought after seeing the previous example that 2/3 is what we multiply by here, but in this particular question, with the way the question's phrased, we're multiplying by 1/3. And 1/3 of 27 meters is the same thing as 1/3 of 27, which is equal to 9. So T1, term 1, after the first bounce, the ball is 9 meters above the ground. So term 2, so after the second bounce, the ball is 27 times 1/3 times 1/3, which is equal to 3 meters above the ground. So what we did was we got 1/3 of 27. So 1/3 of 27 was the height of the previous bounce, so 9 meters. So now we're getting 1/3 of 9, and 1/3 times 1/3 times 27 again gives us 3. Then for term 3, so after the third bounce, the ball is 27 times 1/3 times 1/3 times 1/3, which is equal to 1 meter above the ground. So what we're doing is getting 1/3 of 1/3 of 1/3 of 27. So what's in the square brackets here is what we had after the second bounce, which was 3 meters. So you're now getting 1/3 of 3 meters. So 1/3 of 3 meters is 1 meter. Or you could say 1/3 times 1/3 times 1/3 is times 27, again, gives you 1 meter. So notice that every time we're just increasing by multiplying by another third. And then for term 4, after the fourth bounce, the ball is 27 times 1/3 times 1/3 times 1/3 times 1/3, which is equal to 1/3 meters above the ground. So what we're doing is getting 1/3 of 1/3 of 1/3 of 1/3 of 27. So what's in the square brackets is what we worked out for term 3, which was 1 meter. So you're really getting 1/3 of 1 meter, which gives you 1/3 meter, which is the same thing as 1/3 times 1/3 times 1/3 times 1/3 times 27. So you'll still get 1/3 of a meter. So part 1 asks to find the height of the ball on each of its first 4 bounces. So the height after the first bounce is 9 meters above the ground, after the second is 3 meters above the ground, after the third is 1 meter above the ground, and after the fourth bounce is 1/3 of a meter above the ground. So we have 9 meters, 3 meters, 1 meter, 1/3 meters, dot, dot, dot. So part 2 says, hence, write down the height of the ball after the 10th bounce. So we're just going to follow the pattern that we had. So term 10, so after the 10th bounce, the ball is going to be 27 times 1/3 to the power of n. So it's going to be 27 times 1/3 to the power of 10, because we're looking for the 10th bounce. And that gives us 0.00046 meters. Part 3, after which bounce will the ball be at most 2.5 meters above the ground? So Tn is equal to 27 times a third to the power of n. So we have that from part 2. And after which bounce really means how many terms. So i.e. we have to find n. We have to solve for n. So we're going to replace Tn with 2.5. So the 2.5 representing 2.5 meters above the ground. So that's equal to 27 times a third to the power of n. So we're trying to solve for n, get n on its own. So we're going to divide both sides by 27 to get rid of the 27 on the right-hand side. So that gives us 5 over 54 equal to a third to the power of n. So we're going to use logs. So we're going to have log base a third. 5 over 54 is equal to n. So this is the scorpion tail method in reverse. So a third to the power of n is equal to 5 over 54. Which we can rewrite as log base a third 5 over 54 is equal to n. So we're just going to put this into the calculator. And again, just showing you the scorpion tail method. So the third to the power of n is equal to 5 over 54. So into the calculator, n is equal to 2.165956 ... So since the number of bounces must be discrete data, so discrete meaning a whole number, so you can't have 2.16 terms, you can't have 2.16 bounces, it doesn't make sense. Just like if you had a classroom, you're going to have 30 desks or 31 desks, you're not going to have 30.16 desks, for example. So it has to be a discrete data. So after 2 bounces, the ball will be above 2.5 meters. So after 3 bounces, it will be below 2.5 meters. And that's what we're interested in. We want to know when will the ball be at most 2.5 meters, at most 2.5 meters. So going no higher than 2.5 meters. So we're interested in when it bounces to a height that is below 2.5 meters. So although the ball does bounce up and down, so it is moving between different heights every time it bounces, we're interested in the point at which it gets to when it moves back up. So when it bounces back to a certain height, they're the exact points that we're interested in. So again, after 2 bounces, the ball will be above 2.5 meters. So it's after 3 bounces that it will be below 2.5 meters. And it doesn't matter what the exact height it is that it gets to at 3 bounces. That does not matter, so long as we know that it's just below 2.5 meters. It's some point below 2.5 meters.